Greetings of the day. I warmly welcome you once again to an exciting and novel session of learning. In the previous video, we discussed the historical perspective of Fermat's last theorem, highlighting how a seemingly mysterious marginal note evolved into one of the most challenging problems for mathematicians over more than 350 years. According to Fermat's statement, the equation x raised power n plus y raised power n is equal to z raised power n has no solutions in positive integers for powers greater than 2, and he famously claimed to possess a truly remarkable proof which he did not record. After centuries of efforts by numerous mathematicians, the theorem was finally proved by Professor Andrew Wiles, who provided a highly sophisticated and complex proof, earning global recognition for his remarkable achievement. In the present discussion, we take the problem in different direction and explore certain unique relationships associated with it. Our aim is to share these insights by examining the equation from an alternative perspective. We begin with the working assumption that Fermat's last theorem holds true for all relevant cases, and then proceed to derive interesting results using various statistical and mathematical techniques. Let's begin by considering an equality and analyzing it through a mathematical programming problem. Let's now rewrite the given equality in an alternative form by introducing an error term denoted by E, such that the total deviation from exact equality is captured by this term. Using the concept of mathematical programming, we formulate an objective function aimed at minimizing the error E subject to the given quality, subject to the given equality constraints, and the condition that all variables take integer values. After solving this mathematical programming problem for different values of n, we get a unique relationship. Means if we see this table, it means 1 raised power 1 plus 2 raised power 1 is equal to 3 raised power 1, and the error term is 0 because it satisfies the equation fully. Now 3 raised power 2, 4 raised power 2 and 5 raised power 2 is equal to 5 raised power 2. So here also error is 0. It means that for n2 the equation satisfied fully. For n is equal to 3, it is 5 raised power 3, 6 raised power 3 is equal to 7 raised power 3. Actually, this is not exactly equal to 7 raised power 3. There is an error E which is 0.01. But one interesting thing happened here. This becomes a sequence of the numbers. Starting from this is 1, 2, 3, 3, 4, 5, 5, 6, 7, 7, 8, 9, 9, 10, 11, and continue. As the value of n increases, the sequence goes on. Every time you will see the error remains approximately close to 0.01. This suggests a recurring pattern that provides a possible approach to approximating the given equation. This is the one form of the using mathematical programming problem. Furthermore, we may also examine the problem from another perspective, considering the case where the equality holds exactly, and reformulate the expression accordingly. Let us take the variables y1, y2, y3, and yn be m finite number such that y1 less than equal to y2 and continue. The powers also remains under the same inequality. Now here we see y1 raised power n, y2 raised power n, y3 raised power n, and so on is equal to z raised power n. Here n is equal to m and both are greater than equal to 2. On solving this pattern, we'll see one more interesting relationship, that is for n is equal to 2, sum of two terms is equal. Square of the sum of two terms is equal to the square of 1. Similarly, for n is equal to 3, we need 3 terms. For n is equal to 4, we need 4 terms, and so on. In higher ups, it's true for all values also. It means for 7, n is equal to 7, it is add up 7 terms, and for an 8, so 8 terms in ascending order. It means we identify an interesting structural relationship. The square of a number can be expressed as a sum of the two squares, the cube of a number as the sum of the 3 cubes, and more generally the fourth power as the sum of 4 fourth powers, and so on. This pattern indicates a broader framework in which powers of a number may be decomposed into sum of like powers of multiple terms. Mathematicians are already working on these patterns, but we have found a different pattern and different techniques by using mathematical programming problems, and the pattern is not in haphazard manner, it is simply an increasing order. This work represents a novel and explanatory attempt to view the problem from a different angle. It is with this spirit that we share our findings with a wider mathematical community, in the hope that this modest contribution may inspire further researchers and encourage mathematicians to explore alternative perspectives. Indeed, many problems in mathematics can yield new insights when approached through diverse field methods and innovative thinkings. In our next video, we will bring an exciting application of statistics in disaster management, highlighting how statistical tools can make a real difference in critical situations. Until then, keep learning, stay curious, and have a wonderful day ahead. Thank you. Thank you very much.